Hello, physical science students. I'm posting this video on May 7th. And I want you to have your notes that you've been taking your notes on, your papers that you've been taking your notes on. You should have a pretty good little set of notes on the history of our current atomic model that we embrace. I did another video I posted this morning, yesterday morning actually, on how the models progressed over time from Dalton all the way up to the Heisenberg uncertainty model. Anyway, so just to kind of wrap up or whatever the atomic history, let's just go ahead and enjoy this.
Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Dalton did experiments, said, I think it's clear, atoms are tiny indestructible spheres. Thomson worked with cathode rays, said, I disagree. A plum-pudding model makes much more sense to me. A new chapter in atomic theory started to unfold when Rutherford played around with atoms made of gold. When a few of his alpha particles came bouncing back, he hypothesized the nucleus had knocked them off the track. Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg, many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Bohr saw spectral lines for hydrogen and said, it seems to me electrons move in orbits with specific energies. Heisenberg said, forget it, there's no way to know the orbit or a path where the electron's gonna go. Schrodinger used lots and lots of fancy mathematics, made a model of the atom based on quantum mechanics. It has orbitals, and those are based on probability. The atom is a fuzzy blob of pure uncertainty.
Everybody now.
Thomson, Rutherford and Bohr, Schrodinger and Heisenberg and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Dalton, Thomson, Rutherford and Bohr, Schrodinger, Heisenberg.
Well, I thought that was awesome. Okay, so I'm going to show you guys some questions about the history of atomic structure before we get into, we're going to delve into the nucleus and see what's there, what subatomic particles are there. So just try to answer this as best you can. It's not something that's graded. There are questions on our daily quizzes that are a lot like this, but I think that this will give you an idea of what it is that I'm looking for as far as what you should know about atomic history. This is all notes we've taken, skipping. Cathode ray. Got it. More, yep. Still going. So try to answer this. I'm just going to go through them very, very slowly. Write your best guess. And if we were in class, you would probably have this quiz up on the screen. See how you do. The smallest particle of an element is called a what? Atoms of the same element are alike, said who? Who said this? Part of somebody's theory. 3, what was the term that Democritus came up with to describe the parts of matter that were uncuttable? I don't know that I emphasized this. We shortened it to atom, but he came up with atomos, which means uncuttable. So you might not know that one. But if you had atom, I'd take it. He was the first one to coin that term. Who discovered the electron? Who discovered the nucleus? Let's back this up. Okay, so let's go through. You've had a chance to answer these. If you haven't, pause it and then start it again. I'm going to give you the answers. The smallest particle of an element is called an atom. 2 atoms of the same element are alike, said Dalton. That's part of Dalton's atomic theory. Number 3, like I told you, is atomos. Number 4, who discovered the electron? That's Thomson. Who discovered the nucleus? Rutherford. Who used this for their discovery? Write your answer to number 6. And again, these are things I would expect you to know on a test, and we do have a test coming up. Your final in this class is going to be a test over atomic structure. So let's go back to that one. The person that used this is the cathode ray tube. This was Thomson. Number 7, who used this for their discovery? Hopefully you guys watched those videos that I posted. They do a much better job explaining how this works. The answer, if you're not ready for it, pause it. If you are, the answer, this was Rutherford. This is what he used to discover a nucleus. That something very hard and positive and dense was in these atoms of gold that would cause these alpha particles to bounce back. Whose model is this? So look at that. Tell me what you think. The video that I put this morning where I was drawing these might help you. Whose model is this? So number 9, whose model is that? And number 10, whose model would be this? So let's go through these. If you don't quite have the answers, pause it. If you do, these are the answers. This one with these levels, this is Bohr. He discovered this as spectral lines from hydrogen, that the electrons aren't just outside the nucleus, they're actually in things called energy levels or shells according to how much energy they have. Remember that when he surmised that when an electron had a lot of energy, it was on an outer level, then when it fell back down to a lower level, it emitted light. And the fact that hydrogen could emit many different colors of light told you that there were different levels that they were falling from. Number 9, whose model is this? This was Thomson's model. He knew there was a negative aspect when he discovered the electron, but he knew there had to be a positive as well because matter in general is neutral. And then whose model is this? This is Rutherford. This is where the electrons got out of the plum pudding and he just stuck them outside. All right, so those are things that you should know. Now, let's talk about how small atoms are. I'm going to give you some analogies here. A penny has about 2 × 10⁻22 atoms in it. If a penny is 100% copper, it's going to have 2 followed by 22 zeros of atoms in there. Penny's not very big. That's a big number. That is 20,000 billion billions in just a penny. It's written like that. Big old number. Aluminum is an averaged sized atom. Pretty average. We have bigger ones. The bigger the nucleus, the more energy levels. And this is the whole atom. The nucleus itself is even way smaller, like 10,000 times smaller. But it has a diameter of 0.3 centimeters. That is 100 millionths of a centimeter. So if we take our little centimeter, okay, centimeter is about as wide as my fingernail. I'm trying to get this. And we take that 1 centimeter, that wide from my finger to the end. Divide that into 100 million equal parts. 3 of those is the diameter of an average size aluminum atom. Wrap your brain around this. There are as many atoms in a teaspoon of water as there are teaspoons of water in the ocean. That seems like it might be a little far-fetched, but I read it somewhere. I gotta get a drink of water. My voice is kind of starting to crack. Channeling my inner Ritzman, my gallon of water. Basically, they're really small, all right? Let's look at the nucleus. How many particles are in the nucleus? A bunch, over 200. And you're saying, now there's just like 3 subatomic particles, Mrs. Kennedy. Well, those are the 3 that we really worry about, but there are a lot of others. There's muons, bose, leptons, quarks. I'm going to narrow it down from 200 to 2. So we have the proton and we have a neutron. That's in the nucleus. We're only dealing with the nucleus. We're not dealing with the electron cloud, which, big surprise, the electrons found in the electron. But we're just talking about the nucleus. Let's talk about the differences between each one of these particles. These facts that I have down in bullet form, you're going to want to know about this. You're going to want to know that a proton has a mass of 1 AMU. Now, this unit, AMU, stands for, write this down, atomic mass unit. And it's a special unit that was made just to measure protons and atoms. It's really small. We normally would use grams. We would normally use kilogram because that's the fundamental unit, but grams make a little bit more sense. But it's so small, it's this much of a gram, 1.673 times 10 to the negative 24 grams. So what this is going to look like is you're going to have 23 zeros on the left side. If I move this decimal over, I'm going to have to move it over 24 times, put in 23 zeros. That's just too, so we just said this right here, 1.67 times 10 to the negative 24th grams, we're just going to call it an AMU. It's kind of like saying, I'm so tired of counting eggs, so we're just going to say 12 is a dozen. Let's just use a dozen for that. Only this is a smaller unit. So an AMU, atomic mass unit, was made just to measure the mass of protons. It has a charge of +1. One proton has a charge of +1. It's very important that you understand it's not just plus, it's +1. This is quantified. Because later on when we're doing whether or not atoms are neutral, that +1 is going to make a difference. The number of these, the number of protons, identifies the element, and it's called the atomic number. This is a term that you are going to have to know. Atomic number, this is, I'm going to highlight it if I can. I'm not very good at using this, but so, okay, there. Atomic number is one of those words you're going to want to know. The atomic number, by definition, is the number of protons. And what does it do? It identifies the element, what it is. So, for example, the atomic number of hydrogen is 1. The atomic number of helium is 2. Helium has 2 protons. That's what makes it helium. The atomic number of lithium is 3. The atomic number of beryllium is 4 protons. Add another one, we're going to have boron, atomic number 5. And we've got carbon with 6, and nitrogen with 7, and oxygen with 8, blah, blah, blah. Okay. Very, very important term, atomic number. It's the number of protons. This is going to be the whole number that you find on your periodic table. You have a periodic table. If you have the same one that I sent with you, this periodic table, all right, you're going to find that there's there's a few different numbers on there. The simplest ones basically have two numbers. One is going to be a decimal number, and one is going to be a whole number. The whole number is the atomic number. On the periodic table that I gave you, I can't remember which one I gave you, but it's not always found in the same place on every periodic table. The one that I'm using, the Army one, it's in the lower left-hand corner. Sometimes it's at the top in the middle. Sometimes it's upper right-hand corner. But if it's a whole number, meaning no decimals, that's the atomic number. The entire periodic table is organized by atomic number. It goes from 1 to, we've got a whole 120 by now. Only 92 are found naturally in, the rest of them are made in the lab. But anyways, now let's talk about neutron. It also has a mass of 1 AMU. So they weigh the same in terms of AMUs, atomic mass unit. But if you take it down to what it is in grams, you'll notice that it is slightly heavier, slightly more massive. 1.675 times 10 to the negative 24, as opposed to 1.673 times 10 to the negative 4. A proton, I told you that there's 200 different subatomic particles, all right? Protons are made up of even smaller things called quarks. A quark, there are five flavors? 6 flavors. There's up quark, down quark, top quark, bottom quark, strange, quark, and charm. There's 6 different, they call them flavors. I don't know, whoever was doing this had been up way too long. Or maybe they'd been quarantined, I don't know. But anyway, a proton is made up of 2 up quarks and a down quark. And a neutron is made up of 2 down quarks and an up quark. And so I surmised that down quarks are slightly more massive than up quarks, and that's what gives the neutron a slightly heavier mass. But for all intents and purposes, 1 AMU, they're equal. Okay, that's not that much of a difference. The neutron does not have a charge. It is neutral. It has no charge at all. Another thing, sometimes people say that a neutron is a proton that captured a high energy electron. And that would give it a slightly more massive edge, and it would also make it neutral. I don't know about that. That's getting a little deep for me. But just know that a neutron is neutral. Start of the same thing. Neutron, neutral. It has nothing to do with the identity. It doesn't matter how many protons, or excuse me, it doesn't matter how many neutrons there are. We only count protons. They do, when you add neutrons, you add to the mass, and it can change the stability of the electron. We have different versions of atoms of an element called isotopes that we're going to get into later. And some of them, the stability gets a little shaky when you add too many neutrons. Another very important thing you need to understand is that if we add up the number of protons and neutrons, and I hope I have this thing here that's, okay, let me move that. The number of protons and neutrons together is called the mass number. That is something else we are going to want to remember. Mass number is number of protons and neutrons. It's a little bit harder to find because you are not going to find the mass number on the periodic table. It's not there. The mass number is something that you have to be told. It's the mass number for one isotope of carbon is 12. Carbon is carbon because it has 6 protons. Some versions of carbon also have 6 neutrons. You add that together, protons, the 6 protons that make it carbon, plus the 6 neutrons that it has. You add that together, that's 12. That's our mass number. But again, we talk about isotopes later on. Now, here's what I'm going to have you do. I am going to have you fill in, get a separate sheet of paper, and I want you to fill in this table. Oh, actually, first I wanted to show you, if we were at school, this is what it would look like. I could only teach one of you at a time, so you'd just be one lonely little student in a room all by yourself. But I saw this and, oh man, I miss my classroom. There's my map. There's my desks. This is when I had them in rows instead of pods. Anyway, now I want you to make a chart like this. All right, make a chart just like this. And you need to have the heading for this one's element. Then we got mass number. Pound sign or hashtag P is number of protons. This is number of neutrons. And then you need 1, 2, 3, 4, 5, 6 things. It can be just the thickness of a lined piece of paper. I'm going to give you a little bit of homework. And then I'm going to give you the answers on tomorrow's or the next day's video. The next video that I do, which will be tomorrow's Thursday, Friday, I'll give you the answers to this. So here's what I want you to do. I'm going to give you the mass number and the name of an element. So for example, the first one is tungsten is the name of the element, and I'm telling you that it has a mass number of 184. Write that in. Francium is, I can kind of give you an idea of where these are located. Tungsten is a transition metal. It has a really stupid, its abbreviation, its symbol doesn't start with a T. Francium is an alkali metal. Then I want you to put copper. Copper is a transition metal. It's found near the top. Transition metal, remember, are those short little families in the middle. We did the periodic table, didn't we? Maybe we didn't. Yeah, I had you color it. Yeah. Okay, anyway, chlorine is a halogen over on the right-hand side. Next one, silicon, that is a metalloid. It's going to be near that zigzag line over on the right. And then uranium is a actinide. Those 14 families that are found at the bottom. So if I were, I'm not going to do any of these for you. I'm going to show you how to do them with, and I want to do black. Okay, so if I had, let's pick my favorite one. Let's pick potassium. It's hard to write neatly with my fat finger on this, but so I'm going to find potassium. It's okay, that's why it's my favorite. It is a alkali metal, so I find it over on the left-hand side of the periodic table. I'm going to tell you that potassium has a mass number of 40. So this is how I would fill this in. I find potassium on the periodic table. He's over there, he's in the 4th period, he's right below sodium, and I see on my periodic table that its atomic number is 19. It has 19 protons. That's what makes it potassium. Now remember that this number right here, that is the mass number. That tells me the number of protons and neutrons. So if I have 40 protons and neutrons, and I have 19 of them are protons, they have to be in order for it to be potassium. What's left over to be neutrons? What's 40 minus 19? Used to be 21. That's all we're doing. This is all you're going to do for this. Tungsten, who has a mass number of 184, tell me the number of protons. This isn't going to change. This is what you've got to calculate. You get this from the periodic table. That's all I want you to do. And I will see you tomorrow. See you on the other side.